Hello, my name is Caitlin Fix, and this is the third lab for Physics 2212, where we'll be analyzing the magnetic field of a bar magnet. The purpose of this experiment is to measure the distance dependence of the magnetic field due to a bar magnet. Then we will compare these results with a computational model generated using the PHYS law. We will conduct this experiment using a small bar magnet and a magnetometer sensor on a smartphone. As you will see, the experiment will yield an experimental distance dependence of negative 2.7313 meters and a magnetic dipole of 3.571 am squared. Additionally, the computer model we created very closely resembles the data collected during the experiment, with only minor discrepancies. For this lab, we'll utilize a couple of fundamental physics principles. The first is the Biot-Savart law, which says that the magnetic field, B, is equivalent to mu naught over 4 pi, or 1 times 10 to the negative 7th, times 1 over r cubed times 3, times the dot product between mu and r hat, times r hat minus mu. The next two equations pertain to distance dependence. The first says that the magnitude of the magnetic field of the bar magnet is equivalent to k times r to the nth power. The second states that the natural log of the magnitude of a magnetic field is equal to the natural log of k plus n times the natural log of r. Throughout all of this, r refers to the distance between the magnet and the magnet sensor within the cell phone. Now we are going to move into the data that was collected throughout this lab. We conducted 5 major trials where we found the distance between the cell phone and magnet that produced specific magnetic field X values. These 5 values were 20, 70, 120, 170, and 220. Each of these trials were conducted 3 times, with the final numbers being averaged together. The Excel sheet then calculated the natural logs of the distance and the X values before plotting them on a graph and generating a line of best fit. The second part of the experiment centered around measuring the off-axis magnetic field at a 45-degree angle, to be more specific. During this experiment, 2 key observations were made. The first is that when the magnetometer is far from the magnet, it measures a near-zero magnetic field in the x direction. Similarly, the second states that as the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. Now that we have all of our data, we can solve for the distance dependence and magnetic dipole moment. To find the distance dependence, we can just use the slope of the line of best fit. For this experiment, this yields a value of negative 2.7313 for n. For simplification purposes, we are going to estimate n as negative 3 for the magnetic dipole moment calculations. To find k, we can also use the graph. The y-intercept is equivalent to the natural log of k. So by computing e to the power of negative 14.152, we can gather a k value of 7.1427 times 10 to the negative 7th. Then, by setting k times r to the power of n equal to mu naught over 4 pi times 2 mu over r cubed, we can solve to find mu. This yields an answer of 3.571 am squared. That concludes all of the calculations, and now we can generate the code. This includes defining constants, for example mu naught over 4 pi as 1 times 10 to the negative 7th, and creating the magnet. Additionally, we are going to input our previously calculated magnetic moment, 3.57135. Now we have to define our function. This function details how to calculate the magnetic dipole using the Biot-Savart law. We also had to set a scale factor and distance from the origin. After that, we can set up the observation locations for each of our arrows and create an on-axis magnetic fields using the dipole B function. One of the major aspects of this code was creating the 4 arrows that represent the magnetic field perpendicular to the axis, also using the dipole B function. Finally, we can insert the experimentally gathered d-perp value of 0.16677 and create the arrow that represents the magnetic field 45 degrees off-axis. In this computational model, orange arrows demonstrate the on-axis magnetic fields, the blue represents perpendicular magnetic fields, and the singular magenta arrow demonstrates the 45-degree angle magnetic field. When comparing our experimental and computational values, it is obvious that they are extremely similar. For example, there is only a 0.017 meter difference between the d values. The largest difference between the 45-degree magnetic field is that our computational model omits the z value, unlike the experimental vector. Any other discrepancies between the data could be due to human error when collecting information, or malfunctions within the magnetosensor app. Before coming to the end of the lab, we have a couple of reflection questions to answer. The first asks what would happen if we had laid the meter stick at some intermediate angle with respect to Earth's magnetic field. Overall, if we had not oriented the setup to compensate for magnetic north, our data would have been much different. Instead of only looking at the magnetic field generated by the magnet, we would have been looking at the interactions between the magnet and Earth's magnetic fields. More specifically, the x value would not have started at 0. The second question inquires as to the changes that would occur if we use two identical magnets stuck together, rather than a single one. In general, the two magnets would have combined to produce a more powerful magnetic field. It is possible that the magnetic field would have doubled, but experimental and computational models would have to be created in order to confirm this theory.